afternoon, classmates. So I will be discussing how the design equations for the cooling tower was developed. So here is an illustration of the cooling tower. As we have seen in the video a while ago, the water comes in from the top and leaves at the bottom, while the air comes from the bottom and leaves at the top. And we have L2, which is L2 and L1, which is the mass flow rates of the water, and TL2 and TL1 are the temperatures of the water, and the HL2 and HL1 as the enthalpies of the water. And on the other side, we have Psi1 and Psi2, which is the humidity of the air, and HV1 and HV2 are the enthalpies of the air, and TB1 and TB2 are the temperatures. V1 and V2 are the mass flow rates of air, and V prime is the mass flow rate of dry air, which is constant. Z is the tower height, and this shaded region here is a differential area, and while dz is the differential tower height. So in setting up the overall mass balance, assuming steady state, we have V1 plus L2, which is the entering air and entering water, is equal to V2 plus L1, which is the exiting air and the exiting water. Rearranging, we have L2 minus L1 is equal to V2 minus V1. In setting up the water balance, we have Psi1, V prime, which is the water in dry air, and L2 is the mass flow rate of the water entering, and we have Psi2 V prime plus L1, which is the water leaving the tower. Rearranging, we also have L2 minus L1 is equal to Psi1 minus Psi2 V prime, and there. We also have to set up the enthalpy balance of the tower, of the cooling tower. We have Q, which is the heat absorbed from the surroundings, and HV1 times V prime, which is the enthalpy coming from the entering air, and we have L2 HL2, which is the enthalpy of the water entering, and we have HV2 V prime, which is the enthalpy of the exiting air, and L1 HL1, which is the enthalpy of the exiting water. Rearranging, we also have Q plus L2 HL2 minus L1 HL1 is equal to HV2 V prime minus HV1 V prime. Factoring out V prime, we have HV2 minus HV1 times V prime. So let's now consider the differential area having a differential tower height Z. Coming in from in the differential tower height, or the differential area, we have V prime, which has an enthalpy of HV and humidity of Psi. And exiting, the mass flow rate of dry air is still constant, while the enthalpy is increased by dHV, and the humidity is also increased by d psi. On the right side, we have the entering water, which will have L plus DL, since we set this up as 1 and 2. So here the flow rate is L plus DL, and the enthalpy is HL plus DHL, and the leaving water is LHL. So setting up the water balance, we have B prime psi plus L plus DL is equal to B prime times psi plus D psi plus L. So rearranging and cancelling L and B prime psi, we have DL minus B prime D psi. And setting up the enthalpy balance, we have HB B prime plus L plus DL multiplied by HL plus DHL is equal to HB plus DHB multiplied by B prime plus LHL. So distributing this term here, we have HB B prime plus LHL plus LDHL plus HLDL plus DLDHL is equal to, distributing again B prime to this term, B prime HB plus B prime DHB plus LHL. And cancelling the like terms, we cancel this LHL and B prime HB. We have LDHL plus HLDL is equal to B prime DHB. And from math, we have learned that this is also equal to DLHL, which we will just use the multiplication product rule. There. So from the previous slide, the L can be the average of L can be used, and that is equal to L1 plus L2 over 2. Thus, we will obtain the LHL is equal to DL average times HL, which in which the L average is constant, so we can take it out of the derivative portion. Thus, we have L average times DHL. And HL is also equal to CL, which is the specific heat, multiplied to the TL minus T0. And TL is just the temperature of the water, and T0 is the temperature of the reference temperature. And we have DHL equal to CL DDL. And equating it here, we will have DHL minus L average CL DDL. And another equation is HB is equal to CS, which is the humid heat multiplied to TB minus T0 plus lambda naught times psi. In getting the derivative, we have DHB minus CS dTB plus lambda naught d psi, and multiplying B prime to both sides, we have B prime DHB plus B prime times the whole term, which we will have B prime CS dTB plus B prime lambda naught d psi. And this term here will represent the heat transfer due to convection, and the other term represents the heat transfer due to vaporization. And Justine Melbourne will continue the discussion on heat transfer due to convection and due to vaporization.
For the heat transfer due to convection, we are going to consider again a differential area with the differential height.